Hello everyone. Last class we talked about introduce the new data structure hashing, and we talked about collision resolution. So in collision resolution, there are several methods for dealing with collision resolution: separate chaining and open addressing. So last class we talked about the method of separate chaining. So in the separate chaining, the idea is to keep a list of all elements that hash to the same value. So we saw the example that for the separate chaining, the array element is going to be a pointer, okay, and this pointer is going to point to the list of numbers that maps to the same hash value. For example, all the hash value that is going to map to the hash value 0, they are going to point to these values, this list here, okay. And all the values, for example, like 181, these two values, the hash key for this hash function, the hash value will be 1. So that element of 1, index 1, is a pointer that is going to point to a list where the elements are 81 1, okay. For those value, the hash value is same. So let's talk about analysis of separate chaining. So in the analysis of separate chaining, the thing is that you can see that we need we need a we need an additional data structure, okay. So we need to use list. So each array element is a pointer which will point to the first element of a list, okay. So it's likely that we have to use an additional data structure, and probably we can actually, I mean, the best thing to use implement the list is using data structure linked list. All right. So another thing is that to analyzing the separate chaining, another thing is that what will be the cost of successful search or unsuccessful search. So let's analyze that. So we're going to know about a new term known as load factor, okay. We denote the term using this symbol, load factor. The load factor is a ratio of number of elements n in the hash table to the hash table size, which is n divided by table size. So n means actually number of elements in the hash table. For example, in this example, we have 1 2 3 4 5 6 7 8 9 10 10 elements in the hash table, and the size of hash also 10, okay. So here the load factor is 1, okay. But if there is a lot of numbers in the hash table, I mean, looks like there will be actually a lot of collision. In that case, the number of n could be greater than table size, okay. So the load factor means actually it's the average length of the list is known as the load factor, okay. The average length of a list is known as a load factor. So here, what is the average length, okay. There we have couple of list 0, we have couple of list the size is 2, we have one list size is 1, okay. Now the average length of list, here we have 1. So load factor, here the load factor is 10 divided by 10, okay. But if we add couple of more numbers, for example, let's add couple of more numbers like 92, 96, say 106, 90, like that, okay. So in that case, there we are going to add couple of more numbers. Here we have to add like 91, okay. So then 96 will be added here, okay. It will be like that. So 106, it will be also added here before 96. We have to add actually 106 before 96, okay. and 90, this will be added here. Alright, so last class we discussed about that when we are going to insert a new value, we are going to insert that at the front of the list so that the cost of insertion becomes 1. Okay. Alright, so in that case the load factor here is we have 10, 11, 12, 13, 14, 14 divided by 10, so which will be 1.4. Okay. Alright, so the load factor actually gives us the idea about the average length of a list. Now the chaining, for chaining the load factor could be greater than 1. Okay, and in that case actually the searching cost could be also greater than 1. All right, so the cost of successful searching could be greater than 1. Okay, so in the separate chaining the cost is, we have the cost time. The cost is actually we need the time to evaluate the hash function, which is a constant type. So evaluate the hash function is just one function. For example, if the hash function is x mod 10, it's just one function and it's the time to evaluate the function is constant. So the cost is going to be constant time to evaluate this hash function plus time to traverse the list. Now the time to traverse the list means we have to know the size of the list. What is the average size of the list? So the average size of the list is known as load factor. Okay, so for an unsuccessful search we may have to traverse the entire list, so we need to compare the load factor nodes on the average. Now for a successful search, the list containing one node that stores the search items, okay, plus 0 or more other nodes. So the item we are looking for, it will be in the list that stores the searched item that we are looking for, and that could also store multiple other items, okay, other nodes. So the expected number of other node here is n minus 1 divided by m, which is actually essentially the load factor. So the load factor is n divided by m, but n minus 1 divided by m is also same as, actually it's almost like the load factor. So on the average we have to actually check half of the nodes while we are searching for a certain element, and the average search cost will be 1 plus the load factor divided by 2. Okay, so for separate chaining, the thing is that actually the size of the table is not really important. The important is the load factor. Okay, so what will be the searching cost? That depends on the load factor. All right, if the average length of list is high, in that case the cost of search will be also high. All right, it depends on the load factor. So table size should be as large as the number of expected elements in the hash table. So we want to keep our load factor around 1. Okay, so for separate chaining, the main disadvantage of separate chaining is that actually we need an additional data structure. Okay, all right, so what we want actually in the separate chaining, you saw actually there are a couple of array element is empty, and there are a couple of array element where the list size could be large. Okay, so maintaining another additional data structure, it could be also like a overhead. So we can actually now think about the collision resolution with some other method. So one other method is open addressing. So in the open addressing we have actually two methods. In the open addressing we are going to use linear probing or linear probing, okay, and quadratic probing. So in these two methods we are not going to use an additional data structure, means we are going to actually we are going to do the collision resolution using the same hash table. Okay, all right, So in the open addressing hashing system, all the data is going to inside the same table. Okay, we have a hash table. So if there is some collision, we are not going to use a separate we are not going to use an additional data structure. Instead of that, we are going to use the same table, and there we are going to find an alternate cell to store the data item. Okay, so let's see what actually we are going to do. So here we are going to use a separate function. Okay, so the separate function, this function, let's say for the usual function we have h of x is x mod 10. Okay, so the hash function is h of x is x mod 10. All right, now for open addressing we are going to actually slightly modify this function. It will look like h of x, this function, okay, plus we're going to add an additional function. All right, mod the table size. Okay, so this 10 actually stands for table size. So mod table size. All right, all right, so let's see how this is going to resolve the collision. So we have two type of open addressing, linear probing and quadratic probing. So let's see first the linear probing. So in this linear probing, the collision will be resolved by sequentially scanning an array. Okay, we are going to sequentially scan an array until an empty cell is found. So in the linear probing, the function f of I, we are going to use the function f of I equals to I. All right. So let's see how this is going to resolve the collision. Let's insert the item 89, 18, 49, 58, 9 into an empty hash table, and table size is 10. So hash function, usual hash function is x mod 10 and f of I is I. Okay, so for linear probing, our hash function will be hash of x, which is x mod 10, plus f of I mod table size, which is 10. Okay, all right, now for linear probing, f of I equals to I, and the value of I could be 0, 1, 2, 3 until the table size. Okay, so we are going to use all of the values. All right, so when we are going to find an empty cell for any I, we are going to use that value. So let's see an example. So we are going to add this key 89, 18, 49, 58 and 9. Okay, so we're going to use 89. All right, so for hash 89 10 means hash. All right, so hash 89, if we use hash 89, which is 89 mod 10 equals to 9. Okay, so let's see, we have just an empty table 9, which is an empty table, so the cell 9 is empty. We're going to include 9 here. All right, so then 18, all right, so so 18 is 18 mod 10, which is 8. So 8 is also empty, so we are going to use 8, the cell 8 is also empty. We're going to add 18 here in the cell 8. Okay, all right, now what happens for 49? Okay, so when we are going to add 49, so 49, so the 49, is 9. So the cell 9 is, we have already a value 89 here. So it happens, it creates a collision. Now it creates a collision. Alright. Now how we are going to resolve that? Using open addressing or linear probing. Okay. How we are going to resolve that? Using linear probing. So now we are going to use the hash function, hash of 49 plus f of I mod 10. Okay, 10 is the table size. Now I value, so I value could be 0, 1, 2, 3 until table size. Okay, until table size means actually until actual table size minus 1. So what actually we are going to do, the hash of 49, we know that hash of 49 is 9. So we are going to try first I value with 0. 9 plus 0 mod 10, which is 9. So this one is a collision, so we cannot use that. So then we are going to use I value equals to 1. 9 plus 1 mod 10. So 9 plus 1 mod 10, this 9 is hash 49. Okay, this 9 is hash 49. So now we are going to use the f of I, which can be 0, 1, 2 until the table size minus 1. So now we are going to, first we are going to try with 0, f of I value equals to 0, and we know that f of I in linear probing is I. Okay, so with I 0, f of I will be 0, function of I will be 0. With I 1, f of I will be 1. So with I 1, this value is going to be 0. 10 mod 10, 0. Now we are going to check whether the cell 0 is empty or not. So looks like cell 0 is empty, so we are going to insert 49 here. Okay, so let's now try with 58. So hash 58 value is 8. Okay, so 8, which is another collision. Okay, which is another collision, so we are going to try with the linear probing. So the linear probing should be hash 58 plus f of I mod 10. Okay, so plus first I value will be 0, so we are going to try with, this one is 8, we are going to try with I value 0, which will be 0, which is 8, collision 8 plus 1 mod 10. When as I 0 is collision, we are going to try I with 1. Okay, so I 1, 8 plus 1 mod 10, which is 9. Okay, which is 9, also collision. Then we are going to try with I equals to 2. 0, also collision. We are going to try with I equals to 3. Alright, 11 mod 10, which is 1. Now we are going to add 58 in cell 1. Okay, so we will find that this cell is empty. Alright, so this cell is empty, we are going to add 58 here. Okay, so now can you see how actually we are approaching? So when we inserted 89 here, we found a collision with 49. We actually inserted 49 at the next empty table, empty cell. Okay, we check that the next empty cell for next cell was 0. We'll check that whether it is empty. If it is empty, we are going to insert that here. If this is not empty, we are going to check the next empty cell. Okay, if that is empty, we are going to insert here. If this is not empty, we are going to try with the next empty cell. So try with 9, you will find that this will happen a collision, so we are going to try to resolve with the linear probing. Okay, we add 0. Okay, collision, we add 1, this will be collision, we add 2, this will be a collision. Then we are going to add 9 plus 3. With 9 plus 3, it is going to, I mean with I value equals to 3, it will give us a open cell, which will be our 9 plus 3 mod 10, which will be 2. Okay, we are going to insert 9 here. All right, so you can see that in linear probing we are actually we are resolving the collision by sequentially scanning an array until we find an empty cell. Okay, all right. So in this linear probing, what actually in this linear probing, what happens, we are not using and separate additional data structure. We are using the same hash table, and we are resolving the collision using the same hash table. Okay, we are trying to find an empty cell. All right, we are trying to find an empty cell, sequentially scanning for empty cell, and whenever we are finding an empty cell, we are inserting the value there. Okay, now let's see how actually we are going to find an item in a linear probing. Okay, and we are going to see that in the next segment.